Hello, my dear students. Welcome back to my YouTube channel. As you know that yesterday we had some sort of issues, right? Network issue. So that's why we are taking the class in the morning. But maximum classes we will take in our the regular timings, right? That's 10:30 p.m. Okay. So one thing that you know that we had completed electric field up to the Gauss's law. So today we will be starting our topic, that is my electric potential energy. So let us start from electrical potential energy. Okay, so this was, I guess, electric potential. So let's start now. Once again. So today it is lecture number 12. Okay, so we will start what? First of all, we'll start with the potential energy. We will start with potential energy. Potential energy. Okay, this is my first topic. Potential energy. Okay, so let's start with the potential energy. Okay, so basically, to start potential energy, we will discuss something about the conservative forces. Okay, do you know why? Look, because the potential energy, it is only defined. My potential energy is only defined. This is only defined for conservative forces. Only defined for conservative forces. I guess back in your 11th standard, you had learned regarding potential energy, that is mgh. Okay, so this mgh is defined. Do you know why? Because the force which is behind this mgh, it's my gravitational force. This is my gravitational force, and the gravitational force is a conservative force. If we talk about the spring, what is the potential energy of spring? 1 by 2 kx square. 1 by 2 kx square. Okay, so the force driven it is spring force, F equals to K times X. Conservative force. Done. No? So potential energy is only defined for conservative force. So now, what is conservative force? Now, 1 second. Okay. Now, what is conservative force? If we are talking about conservative force, no, that we need to learn about conservative force. Conservative force. So conservative force means that type of force which only depends on initial and final position. Which only depend on initial and final position. Look at it. If we had a box here with mass m. Now I am taking this box up to some particular height h. Okay. Now my box is here. So what is potential energy of this box? Sir, it is mgh. Okay. Now if I take this box in this way, so what is potential energy of the box? Sir, still it is mgh. So by this particular example, now look, firstly I take this box straight, but in second example I take it in the zigzag way. But in the both scenarios, my answer is same. So it simply indicates it only depends on initial position and the final position. Okay, it doesn't depend on the path taken by the particles. It doesn't depend on the path on which we are applying force. It only depends on the initial and the final position. That's all. And here the potential energy in electrostatic is equals to K Q1 Q2 by separation. So I can write F. What happens to it? One second. I can write F because it depends on the Coulombic force, and Coulombic force, conservative force. Done? Done now. Now we will prove this one. Sir, what is the proof of it? So let us derive this formula now. Let us derive this formula. Okay? Because you all want something for your boards also now. Let us derive the same thing. Let us derive it. Look now. Simple example. If here I have a charged particle Q1, I have charged particle Q1. So around the charged particle, within the vicinity of the charged particle, okay, if we are placing the different charged particle, that charged particle will face a force of attraction or force of repulsion. We know this thing. Why? Because if positive charge is there within the vicinity of the electric field, that particular charge will face what? Force of repulsion. If that is negative, then that particular charged particle will face force of attraction. So here, r distance apart, here now I have charged particle plus Q2. Okay, this is at point A. And distance between them, it is given to us R1. Now, I want to take this particular charged particle here. I need to take it here up to the distance of R2. So initially, my charged particle is R1 distance. Now I need to take it from R1 to R2. Look, beta. Look now. Look now. So I guess for positive ripple, so electric force will be in this way. The Coulombic force, no? So due to this Coulombic force, my charged particle, that is Q2, it will go from A to B. So I guess my B is final position and this A is initial position. We know it now. So what is the work done? There is a displacement also. Look, displacement and force is being applied. I guess there is a work done now. So now I guess work done, I can write work done is equals to force. Work done is, one second, work done is force into displacement. Force into displacement. Okay, but here we cannot use, we don't have to use it now. Do you know why? Look, this formula we can use now when my force is constant. We can use this one when my force is constant. But here you can see now, look, Coulombic force, that is F is equals to K Q1 Q2 by R square. This Coulombic force depends on the separation. More separation, less force. So here you can write, sir, my force is variable, it is not constant. So I cannot use this formula. So instead of this formula, I can use work done is equals to integration force dot ds. And my particle is going from R1 to R2. Look, this is my displacement now. So what is the angle between displacement and force? I guess 0. It is 0. So I guess theta is 0. What is theta? It is angle between F and ds. It is 0. So now if I just open the whole thing, so it is R1, R2. What is F? So force is equals to K Q1 Q2 by R square. I will take a general thing R. That's what a general thing R square. Okay. Then F ds. So I can write ds, then cos theta. Cos theta is 0 degree. It is 0 degree. So I guess I will write work done is equals to, look now, I guess my K is constant, yes sir. My Q1 is constant, yes sir. My Q2 is constant. Now I will integrate from R1 to R2. Integration of only 1 by R square with respect to, here I can write dr. There is no issue, no? dr. And cos 0 is 1. So this is my expression to calculate my work done. Okay. One thing that you need to remember now, that is, this is work done by electric force. Work done by electric force. It came out to be, sir, K, Q1, Q2. And what is the integration of 1 by r square? Sir, I can write integration of 1 by r square with respect to dr. I can write it integration of r minus 2 with respect to dr. So integration of r minus 2 plus 1 divided by minus 2 plus 1. I guess it came out to be r minus 1 divided by minus 1. So which is equals to minus 1 by r. It is minus 1 by r, no? Yes, sir. So I can write minus 1 by r. Upper limit is r2, lower limit is r1. I will take minus outside, it is minus k q1 q2. 1 by r, upper limit r2, lower is r1. I can write, look, minus outside, it is k q1 q2. Then 1 by upper limit minus 1 by lower limit. So I got my expression now that work done by electric force equals to minus k q1 q2. 1 by r square minus 1 by, sorry, it is not r square, it is r2. It is r2 minus 1 by r1. Okay. So what we can do here now? Do you know what is work energy theorem? That is, work done by all forces is equals to change in kinetic energy. Change in kinetic energy. Here, you need to note one thing, that is the acceleration. Acceleration should be 0. Okay. This thing you need to note here, right? Whenever we are dealing with these conditions, no, so we need to slowly drag the particle. Why? If we drag it very hard, no, so there will be a acceleration. If acceleration, then more forces, no, the magnetic force also will be there, right? That will disrupt my electrofield study. So that's why we are taking it very 0, very slowly, constant velocity. Okay, look now. So if no acceleration, v is 0, so it is change is 0. So how many forces we have here, sir? One is work done by electric force. One more is work done by external force. Two things, it is 0. So from this particular perspective, what is work done by electric force? Okay, what is work done by electric force? So I can write work done by electric force is minus delta times u plus work done by external force equals to 0. I can write like this now. Okay, so work done by external force is equals to plus delta U. So here, work done by electric force, I guess it is minus delta U. So I can write minus delta U equals to minus K Q1 Q2 1 by R2 minus 1 by R1. Minus minus cancel out. So I can write change in potential is equals to K Q1 Q2 1 by R2 minus 1 by R1. Okay, now, suppose, okay, suppose, a general case. Now, suppose, I will write suppose in a very big letters. Suppose is, if initial position, if initial position is infinite, that means we are bringing a particle from infinite. Okay, so look, it is my plus q, and here is my infinite. I have a charge particle plus q naught. Let us suppose infinite means here my distance is infinite, and at the infinite position my electric potential energy will be 0. Just note it down. if initial position is infinite, suppose. So what I can write now, what is initial? I guess R1 is initial. Yes, sir, R1 is initial. So R1 I will take infinite. And if final position is R, so what I can write, so delta U is equals to K, Q1, Q2. 1 by R2 is R minus 1 by infinite. 1 by infinite is 0. What is change in potential? Is it final minus initial? Yes, sir. Final potential energy minus initial potential energy equals to K Q1 Q2 by R. And we know that initially my particle was infinite, so it is 0. So I can write electrical potential energy came out to be K Q1 Q2 by R. Any doubts? Any issue about this thing? Easy? Done? So what is basically now electrical potential energy? It is defined for a system, right, where we have multiple charges. Look, if we are bringing a charged particle from infinite to that particular point, if we are bringing a charged particle from infinite to a particular point inside the vicinity of that particular charged particle, so the system is possessing some energy due to the what? Due to the presence of charges. The system will possess some energy now due to the position of these particles. That particular energy is known as what? It is known as electrical potential energy. Electrical potential energy. And it is value is K Q1 Q2 by R. But this is my general formula. Like this is my general. This is my general formula. Okay. And this one is specific. This one is specific because generally we are taking if we are taking about the problems, so 99% you will find if we are taking charge particles from infinite to a particular charge point, right? So there at infinite my distance is infinite, so 1 by infinite is 0, and the potential energy at infinite is 0. So the expression that we got at the end, it is K Q1 Q2 by R. So we now know now what is potential energy definition, what is potential energy equation. Simply it is K Q1 Q2 by R. Okay. And this potential energy is a scalar quantity. Potential energy is a scalar quantity. It is what? A scalar quantity. Whenever you are using electrical potential energy, use charges with sign. Use charges with sign. Done. If we talk about the unit, it is basically a charge. It is basically energy. So energy is joule. Okay, you will convert it in the electron volt also. There is no issue. Done. And potential energy could be positive, potential energy could be negative, potential energy could be 0. Okay, 0 means at infinite is 0. Okay, so these things you need to remember about the potential energy, then. So it is simply a potential energy, but we have a superposition here also. No, if we have a multiple charges, then what we can do, I can write sir K Q1 Q2 R plus K Q1 Q3 by R, sir K Q1, like these things we can do it. I guess we had done this superposition in back our Coulomb's law and back in the electric field also, no? So I guess in this particular topic, I don't need to just derive it, no? So more important, we will do a numerical problems. Okay, we will do what? A numerical problems once again. Okay, we'll numerical problems. Look now. And one more thing, that is potential energy always in pairs. Potential energy, it is always in pairs. So what does this line indicates or means, right? Look, if we have three charged particles, Q1, Q2, and Q3, so my potential will be firstly due to these two, second due to these two, and third due to these two. Done. That's simple. If we have three charges, so three charges will give my three pairs. So look, we have three charges, 1, 2, 3, and we have three pairs also. Now Q1, Q2, Q2, Q3, Q1, Q3. If we have four charges, four charges will give me how many pairs? Sir, six pairs. How many pairs? Six pairs. So how? Look, if we have a square, okay. My charge particles here is Q1. Here I have Q2, Q3, Q4. So if this is my system, no? So how to define its potential energy? Firstly, we have this pair, one pair, two pair, three pair, four. Then I guess we have four. Look, five. We have six pairs. So three charge three pair, four charge six pairs. So now we know how many pairs we will get now. What is the usage of these things? Look, we will do some numericals, then you will get each and every doubt clear. Okay. Look, this numerical was asked in your IIT examination, and that is, if potential energy of my system, that is net potential energy, if it is zero, then find a ratio of Q by Q. Now my system is in this way. Look now. This is my system. Here is my 2Q charge. Here I have plus Q charge. Here I have what? Plus Q charge. This distance is A. So this is A. So you can find the third one now by Pythagoras theorem. It A square plus A square 2A square, that is another 2A only. So how many charges we have? Sir, 3. So 3 pairs. So what will be the electric potential energy of these 3 pairs? Sir, one pair, second pair, then third pair. Okay. So for first pair, what I can write? Sir, K, Q, 2Q divided by A plus, sir, K, Q, Q divided by root 2 plus A plus, sir, K, Q, 2Q divided by A equals to 0. Net is 0, no? Okay, look now. I will take K, Q, Q common. I will take K, Q divided by A common. So what I have now? K, Q by A. So here I guess we have 2Q plus K, Q. I guess I have Q divided by under root 2 plus I guess I have Q. I think 2Q now equals to 0. So this one, and this one, I will take it right side. It will become 0 now. 2Q, I guess 4Q. So I get 4Q plus Q by root 2 equals to 0. So can I write now? I need to Q by Q now. Okay, I will write Q divided by root 2 is equals to minus 4Q. Can I write now from this particular example? Can I write now my Q divided by Q came out to be minus 4 root 2. This one. This is how we can negate it. Okay, so this now look, it is what? For many charges. How to write electric potential energy. Let us do one more numerical. Look, we have three charges, Q, 2Q, Q, L, L. Then same, my potential energy net is 0. Find Q by Q. Find Q by Q. How many pairs we have? Sir, one pair. Sir, one pair. Sir, third pair is this one, right? This one. Okay, so these are three pairs. So how to write now? First equation, K Q 2Q by L. Second one, K 2Q Q by L. Third one, K Q Q divided by 2L equals to 0. One more thing now, look, I will take KQ common, L common, KQ common, L common, KQ common, L common. It will cut now. Then what I left with, it is 2Q plus 2Q plus Q by 2 equals to 0. Yes. Okay. Look now, I can get right now. So I will write 2Q is equal, okay, plus 2 to the 4, it is 4Q plus Q by 2 equals to 0. I can write 2Q plus 5Q by 2 equals to 0. So it's 2 to the 4. I can write 4Q plus 5Q by 2 equals to 0. Then 4Q is equal to minus 5Q. So I guess Q by Q is equal to minus 5 by 4. Q by Q is minus 5 by 4. Okay, done. Okay. So I guess now we are done with electrical potential energy. We had discussed the majority numericals from it. Done, beta? Now let us start. 1 second. We had many topics now. So let us start now. Distance of closest approach or conservation of mechanical energy. Distance of closest approach or conservation of mechanical energy. Na? Distance of closest approach is good. Na? This topic, I will take it. 1 second. Okay. Okay. So which topic we will start now? Distance of closest approach. Closest approach. You will repeat the same thing in your modern physics. Okay, but here is also we need to do it now. Distance of closest approach. Okay, now look, you will find many interesting things here. Look better. Here we have a nucleus, that is positive charge nucleus, which charge is Ze, positive. It is what? It is a nucleus. Look now, nucleus, and this nucleus is fixed. Fixed means we have applied some force. Okay, why? Due to that external force, it is fixed now. Fixed means this particle is at rest. It is at rest. Why? Due to external force. Okay, what is Z here? Z represents atomic number. Z represents atomic number. So here, let us suppose we have alpha particle. Here is my alpha particle, alpha, and I am throwing it with velocity v. Do you know what is alpha particle? It is doubly ionized helium particle. That means if we have helium, and in helium, if we take out the 2 electrons helium, so then the thing that is now in helium, that represents alpha particle. Okay, so the charge of alpha particle is 2 times electron, then with mass m. alpha particle. Suppose, look now, if initially, if initially, initially, if we write initially, if initially my alpha particle is at infinite, I write initial distance between alpha particle and Z nucleus, it is infinite. Infinite separation. These are at infinite separation. Now both are at infinite separation. So what will be the initial potential energy? So it is zero. It is zero. Potential energy of the system will be zero. Why? Because there is an infinite number of what? Distance between them. So I can write U, K, Q1, Q2 by R. R is infinite. 1 by infinite is zero. So U is zero. Okay. Now, when we throw the particle with velocity V towards the ZE, what will happen? I guess the distance between the alpha particle and ZE will decrease. Look, it will come here now. Look, it will come here. So what will happen? Positive charge. They will repel each other. Yes, sir, they will repel each other. But as we know that this particular is fixed, this one is fixed, so it won't get affected. It is fixed there also, right? It doesn't get affected now. So what will happen now? When this charged particle will be here, let us suppose it is here somewhere, okay, here, okay, alpha. So it will face what, sir? It will face my Coulombic repulsion. It is my electric force. Okay, positive repel na. So my alpha particle will get force which is opposite to the velocity. We know that if force is opposite to velocity, so we will write it as a what? It is retardation process. It is a retardation. A retardation means slowing down. It is slowing down. Okay, now look, it is going with velocity v dash now, and some force is acting opposite to it, so it will retard now. It will retard now. So I guess at one particular point, its velocity will become zero. Suppose when my particle reach this particular position, this one now, okay, if its velocity becomes zero, it will become zero now. It will become zero. Why? Because it is coming towards the ZD now. So my magnitude of repulsive force will increase. There will be a point where its velocity will become zero. So this distance, the minimum distance between the alpha particle and your nucleus, the minimum distance known as distance of closest approach. That means beyond this particular point, my alpha particle won't get it. It will go in back then. Okay. So here, my alpha particle speed will be zero. It is zero. Okay. Look now, we have to apply two things: conservation of mechanical energy and conservation of linear momentum. These two things. No? Look, just have a look towards the screen. Remember it. Now we have two things. We have two things: conservation of mechanical energy. Conservation of mechanical energy. So this conservation we can use if we have conservative force here. If we have conservative force. Done. Here in my this particular topic, only Coulombic force is there. Na? Look, repulsion is due to the Coulombic force. So I can write only Coulombic force. Only Coulombic force present. Okay, and Coulombic is conservative force. So we can use conservation of mechanical, COME, conservation of mechanical energy. Second point is conservation of linear momentum. It is what? Conservation of linear momentum. Okay. So conservation of linear momentum. Look, first of all, so we can use conservation of linear momentum when my net external force is zero. Okay, so we can use it now when my external force is zero. we can use it. But here in this example, it is fixed now. It is fixed. If it is fixed, so we had some external force. Yes, sir. So here my external force is not zero. So I can write here, sir, my external force is not equal to zero. If my external force is not equal to zero, so which simply indicates that, sir, we can use the conservation of mechanical energy, but we cannot use the conservation of linear momentum. Done? Okay. So let us use now, use conservation of mechanical energy. Okay. Can I write kinetic energy initial plus potential energy initial? It will be equal to kinetic energy final plus potential energy final. Can I use like this? Okay. So initially we projected our particle with velocity v. So I will write it is 1 by 2 mv square. And initial potential energy is zero at infinite distance. Finally, my particle stops. It is velocity is zero. And what is my final kinetic energy? Sorry, potential energy, sir, K, Q1. Q1 is how much? Alpha particle, na, that is 2e. Q2 is how much? Sir, ZE divided by distance is R naught. So we have to find this R naught. So I can write now, sir, 1 by 2 mv square equals to, I can write Z to, it is K to Z E square by R naught. So I guess R naught is equals to 2 to the 4k Z E square divided by, it would be m v square. Okay, m v square. So yes, sir. So this is my expression of what? Closest approach. This is the closest distance between alpha particle and your nucleus, which is bounded, which is at fixed point. So from this particular figure, what you conclude now? You conclude that my closest approach depends inversely on mass, and it depends inversely of square of velocity. These two things you need to remember. Look now. So we had a numerical back in our IAEEE era, and numerical was like potential is V, it goes change to 2V. Something about it. Sorry. We are not talking about potential, it is velocity. So if we are throwing the particle with velocity V, it has distance R. Okay, closest approach. Now, if the distance goes, if the velocity goes to V, so what will be my new distance? Look here, you can see clearly now we are talking about the velocity. We are talking about the velocity. And velocity and radius, this equation, I can use it. Yes, sir, it is 1 by V square. Okay, so I can write R dash is equals to R by 4. This is the answer. It took less than 5 seconds. It took less than 5 seconds. Less than 5 seconds. Okay, but what we can do right now, let us change the whole scenario. The second particle which were fixed, now let it be now free. Let it be now free. So look now. Here we have one charge particle. Here I have one more charge particle. Done. Charges plus Q. Charges plus Q. Suppose. Okay. Now it is at X point, it is at Y point. Both are free. Look here. Both are free. So I guess we can use now conservation of linear momentum as well. No external force. Now we just throw it with velocity. What will happen now? Look. Initially this particle is at rest. Initially it is at rest. Okay. It is moving. This one is moving. What will happen now? When this particle, the which is at X, when it will be closer to the Y, okay, when it is closer to the Y, okay, this, there will be a force of repulsion, look, plus Q. there will be a force of repulsion. Okay, so this particle will apply force on it like this force, electric force, and this will apply force on it. So by seeing this now, I guess this particle will go in retardation. Retardation. Why, sir? Because velocity is in this way, force is opposite, it is retardation. So it gets slowed down. But here, look, forces is rightwards and it will move towards rightwards only. So I will write it is accelerated. It will get accelerate. This will go retard, this will go accelerate. Now we need to find what? Minimum distance. Initially, if it is infinite, at final, what will be my minimum distance? Look, better what will happen now? What will happen now? Look now. Look now. My particle, look, this one is y, and this particle, I guess my hand is visible to you. Now this particle is at x. So when this particle approaches towards this particle, now look here, Coulombic force activates now. So it will push this one. So it is coming closer. So it get accelerate, retard, and accelerate. Okay. So what is the minimum distance between these two? So there will be at one point now when it is accelerate, it will go on accelerated motion. So it is distance increases. Firstly, distance is this much. Then it decreases. Then it gradually increases. Done now. So we have to find the minimum distance. We have to find the minimum distance. Look, beta. So S relative, the relative should be minimum. It should be minimum. It should be minimum. So let us differentiate it. We know that if we need to find minima, so we will differentiate it. Differentiate my S relative with respect to time. It will be 0. It is. And what is S relative by R? This derivative, it is V relative. 0. So my velocity relative will be 0. So when my velocity will be 0? When there are two things. Both should be in same direction with same magnitude. Same magnitude from collision, chapter of 11th. So my V relative would be same. So I can write now. So if this is my particle charge plus Q, this is my particle charge plus Q. Sir, both should have same, what is? Same direction, same magnitude. So I can write if the velocity of this particle is V naught and it should be V naught. It is only possible when masses are same. Now let's take the masses same. Masses same. Okay, masses same. So here I will get my minimum distance, that is R naught. What is this R naught? We need to get it. So use conservation of momentum. So I will write what? Momentum conservation. I will write momentum conservation. I will write what beta? Momentum conservation. Okay. Momentum conservation means initial momentum is equal to final momentum. Initial momentum is what? Sir, look, initial momentum. It is initial case, no? Look, this particle is at rest, this particle is at rest, this one is motion. X particle is in motion and Y is at rest. So I can write mass of first one into velocity plus 0 is equals to final condition. This is my final condition. Both particles is at rest. So can I write now mass of first one into velocity plus mass of second one into velocity. So I can write mv came out to be beta 2 times mv naught. Cancel out. So my v naught came out to be v by 2. Okay. So this velocity is how much? It is v by 2. This is v by 2. This is v by 2. Done. Now let us use the conservation of energy now. Use what? Second point is conservation of mechanical energy. I write kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final. Initially, one particle is in motion, 1 by 2 mv square. Second particle is at rest. Initially, both are at infinite, it is 0. Kinetic energy final, 1 by 2 mv square, so 1 by 2 mv naught square. Plus second one is also in motion in same direction, 1 by 2 mv naught square. And kinetic, this potential energy would be K. Q1 Q2 by R minimum. So I can write 1 by 2 mv square equals to half of this one. It would be mv naught square plus k q square by R minimum. So I can write yes, I can write here k q square by R minimum. It came out to be 1 by 2 mv square minus mv naught square. So I can write 1 by 2 mv square minus m. What is v naught? It is v by 2. V by 2 square. So it is 1 by 2 mv square minus mv square by 4. So look, I will take, it is 1 by 2 common and mv square also common. I will have 1 minus 1 by 2. So half minus half is half. I will get 1 by 2 mv square into 1 by 2. I guess my answer is 1 by 4 mv square, and here is k q square by R minimum. Done. So what is R minimum now? So R minimum came out to be, it would be 4 k q square whole divided by mv square. This is my minimum distance between two particles. Easy, no? This is how you need to manipulate your numericals to get your answer. Easy? Very easy. Very easy, no? Let's just move forward now. Okay. Look now. Suppose we have two protons. We have two protons. One particle here with charge plus q. Same two protons. Then mass is same, m and m. Distance them is r. Initially, it is initial condition. No? Both are at the distance. We know that it will apply a force Coulomb here, and this one is apply a force Coulomb here. So these are released from rest. These particles are released from rest due to mutual repulsion. Okay, we just put it here now. Then due to the repulsion, they will get apart from each other. Find velocity of each proton when separation between them becomes infinite. So now, when this particle will tend to infinite, at that particular moment, we need to find its velocity. Look here, how we can do it. Look, external force, we are not applying any external force, because when we just release it now, so we take our external force out, then there is no external force, only my electric force is there. Electric force is conservative, so we can use conservation of mechanical energy. External energy is zero, so we can use conservation of linear momentum also. Look now, first thing I will use conservation of linear momentum, which indicates initial momentum equals to final momentum. What is initially? Initially these are at rest. I can write 0, 0. Finally, this particle will go in this way, and this particle will go in this way. Mass is same, charge is same, so velocity will be same, but in opposite direction. If let's suppose it is v1, it would be v2. Okay, I can write minus v2. Or if it is positive, it is negative. No issue. It is up to us, no? So I can write it minus mv1 plus mv2. So initially I will get mv1 equals to mv2. Cancel out. I will write v1 equal to v2. Both equals to v. So velocities are same. Velocities are same but opposite to each other by conservation of linear momentum. Now, one more thing, we can use conservation of mechanical energy. That is kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final. Now kinetic energy initial, both are at rest, I will write 0 plus 0. Potential energy initially both are within the vicinity of each other, na? So there will be a potential energy for sure. And look, only two charges there, only one pair, so I will write only one equation, that is k q1, that is q2, that is q also divided by r, equals to final kinetic energy. It is 1 by 2 m, let's go v1 square plus 1 by 2 m v2 square. Okay, plus at the end the separation will be infinite, so potential energy is 0. So look now, I can write, sir, it is k q square by r. Look here, half vv same, I can write equals to, here I will write equals to, no? It is equals to, one second. Okay, equals to, it is mv square only. I guess I need to get v, na? I guess v is equals to k q square by rm root. Okay, I can write like this. Or look, I will take q outside. Now it is q divided by k is 4 pi epsilon naught. It is r into m. A root is here. This one is correct. This one is also correct. Done. Easy. Easy now. Let us do a couple more numericals. Let's do more couple numericals because we had time now, beta. Yes. Let us do some more numericals. Look now. 1 second. Okay. So let us do some numericals. Look, if initial configuration of my system looks like this, initially sides are 2a, na? Equilateral triangles, Q, 2a. Charges are at the vertex Q, Q, Q. It is my initial condition, initial. Now, what happens? We are bringing them closer to each other. A, A, na? So look now, we know that they are just repelling each other, but by applying some external force, they will come closer to each other. So we will get it as final condition. Final condition. So this is my initial, this is my final. So we have to find out amount of work done. Work done by external force. Okay, work done by external force. So one thing that we know now, that is, sir, work done by electric force is equals to minus delta U, and work done by external forces plus delta U. Delta U is, look here, it is initial condition. So what is initial electric field? What is initial electric field? 1 second. Okay, Now it is initial condition. So what is the initial potential energy? Sir, look, 1, 2, 3. So we have three sides, three charges. So three electric potential energy, right? So I can write K for look, one side, two side, three side. So I will have three. I can write K Q1 Q2 divided by 2A plus K Q1 Q2 by 2A plus K Q1 Q2 by 2A. Both are same. All the threes are same. So I can write 3 K Q square by 2A. Okay. So here, what is K final here? It is final. It will be equals to 3K square divided by A. Done now. So look now, work done by external will be equals to delta U. Delta U is U final minus U initial. U final is 3KQ square by A. Initial is 3K, sorry, KQ square by 2A. So half, it will be 3 by 2 KQ square by A. This is my answer. This would be my answer. This will be my answer. Done? Okay, now let us do one numerical from NCERT. Okay, you will find the numerical in your NCERT also. One second. One numerical is from your NCERT. NCERT. That is plus Q charge particle minus Q charge particle with separation R. Now we change it into this now, plus Q charge particle minus Q charge particle, distance is infinite. What is work done? Look, initially I will write K, one is Q, it is minus Q by R. Final will be K, Q minus Q by R. So U initially will equals to minus KQ square by R. 1 by infinite will be 0. So U final will be 0. So what I can write here now, look better. So work done by external force equals to delta U. It is U final minus U initial. U final is 0 minus U initial is minus KQ square divided by R. So I will get KQ square divided by R. This one is my answer. This one is my answer. Done? Any problem? No problem. Done now. So let us do some numericals also. One second. Okay, done. So let us start now. Electrical potential. Electric potential. Electric potential. Denoted by letter V. Okay. So it is equals to work done bringing a charged particle from infinite to at a particular point divided by the charged particle. Work done is joule. Q is coulomb. Okay. Joule per coulomb. It is also known as volt. What does it mean? Look better. Suppose this is my space. In the space, we have charged particles Q1, Q2. Okay. That means within this white boundaried figure, we have electric field inside it. Okay. Now here at this particular point, here at this particular point, what I have a charge particle. I have a charge particle. And the charge particle's magnitude is 1 coulomb. That is unit charge. I have to bring it from the point here, point P. But condition is slowly. Acceleration is 0. Done? And look here. So we are applying force. So I need to get it here. So I am applying my external force. And here they will just apply a what? electric force, Coulombic force. So if my acceleration should be 0, so I can write, sir, my external force should be equal to my electric force. In this condition, my A is 0. If let us suppose my external is more than electric, okay, so A is not 0. This is not, we are not dealing with it. If my external force is less than my electric force, that means electric is dominant, so my particle will not be at point P. Okay, the push will be more, push will be more, so my particle won't be at point P. Okay, now by somehow I dragged this 1 coulomb charge, this 1 unit charge at a particular point P. Work done in bringing a this charge particle 1 coulomb from infinite to a point P. This work done per charge is known as electric potential. It is what? Electric potential. This is infinite. This is infinite. At infinite, my U is 0. We know this thing. Done? Potential is also 0. Look better. So potential at point P is work done bringing a charged particle from infinite to point P divided by the charged particle that we are bringing. This is my electrical potential definition. Work done in bringing a charged particle from infinite to point P divided by the charged particle. Okay, and it is unit is volt. It is a scalar quantity also. It is a what? Scalar quantity. Done. Look now. Look now. If somehow, if this is my region, this is my region. Okay. Here we have charge particle Q1. Okay. This is my point P and this is my point Q. First of all, my charge particle is here. I will bring it to point P. First condition. What will happen? Sir, there will be a potential VP. There will be a potential VP. It is work done divided by charge particle. Work done 1. Okay. Now same, if I take the charge particle from this point to this point. So I have apply more force. Why? Because more closer to the Q1, so more repulsion to overcome more repulsion to more external force. So I will have VQ. It is W2 by Q. Which one will be more? Sir, VQ will be more than VP. But how much? We know that VQ will be more than VP. How? Because the repulsion at Q will be more than P. But how many times? So what is difference between these two? 1 second. So what is difference between these two? Sir, the difference would be VQ minus VP equals to work done in bringing a charged particle from P to Q divided by Q. This is my potential difference. Potential difference. It simply indicates if we are bringing a charged particle Q to point P, then we are bringing a charged particle Q to Q particle to point Q. So up to this particular point, this one, I have to apply a same energy. I have to apply same force. Then from P to Q, in this region, I need to apply some extra energy, extra force. So let us suppose what will be the external. If it is initial, it will be final then. So potential difference means potential high minus potential low equals to by bringing a charged particle from initial to final divided by Q. It is known as potential difference. Easy or tough, no? Easy or tough? It is way more than easy, no? Very easy. Very easy? Sir, very easy. Done? Okay. Look better. So let's start one more topic known as electric potential due to point charge. Electric potential due to point charge. Here I have charged particle Q. Here is my point P. Distance is R. Distance is R. So if I need to bring a charge particle from this particular position to this particular position, this q naught should overcome. This q naught should overcome what? The repulsion. It should overcome this repulsion. Then it will be at point P. So what is electric potential at point P? Sir, it is K Q with divided by R. So here my potential, electrical potential at any point P is equals to the K times Q divided by R. Very easy, and it is very important that you need to remember it. Very easy and important also. Okay, done. Okay, look now, beta. Let us do a numerical. If this is my square, at each and every corner I have charged particles Q, Q, Q and Q. Side is A. Done. At the center, what will be the electric potential due to all these? Look, the distance is A. So this distance will be how much? A by root 2. All will be the same. All will be the same. So how I can get it? Due to this one, I will write potential at center will be equals to K Q divided by A by root 2. Due to this one, I will write it is K Q by A by root 2. Due to this one, it will be K Q divided by A by root 2. Due to this one, it will be K Q divided by A by root 2. So what is net? So net will be equals to 4 times KQ divided by A by root 2. I will take it up. It will be 4 root 2 KQ by A. This is my answer. This one is my answer. That is one last numerical. Let us complete a one last numerical. Okay. Look here. Charge particle Q, charge particle Q, charge particle Q. At this regular hexagon, my charge particle is Q. Side is A. So this will be also A. Done. So how many charges we have? 6. By each, look, distance is same now. So electric potential by each and every one will be same. Due to this one, it will be KQ divided by A. This one KQ divided by A. This one KQ divided by the 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 A. What is net? Net will be equals to how many? We have 6. So 6 is KQ divided by the A. This is my answer. This is my answer. Okay. I hope you understand the class, and if you have any sort of doubts, you can just ask me. Okay, if not, then we will continue the session in my next class. Thank you, Beta. Bye. Bye. Thank you.